Okay, let's jump into section 8.2. Now, this is going to be very similar. There's some things that are very similar to 8.1, but we are looking at a different type of sampling distribution. The last sampling distribution we did in 8.1 was for sample mean. Today we're going to look at sample proportion. So this is a little bit different, and we're going to have a whole new way to calculate standard deviation. I'm sure you were looking forward to that. Before the next test, before the final test, I'm going to give you a really good breakdown of how to tell the difference between the two. Right now, just realize that in 8.1 we're looking at sample mean, and in 8.2 we're looking at sample proportion. And so we're going to describe the sampling distribution of a sample proportion, and we're going to compute probabilities of a sample proportion. So the point estimate. So suppose that we have a random sample of size n, and we obtained it from a population in which each individual either does or does not have a certain characteristic. So they either are or they aren't, whatever it is. And so the sample proportion, and we call this p hat. Just a second here. So this is a p hat. So it has p with the little upside down v over top of it. So the little point on top. So that's called p hat. And p hat, unfortunately, for some reason, it's not showing up very well here. P hat equals x over n. So it's exactly how we would find when we're finding a proportion, when we're finding a relative frequency. It's the same thing. So this would be your number of successes and over the number of trials. And it's not necessarily number of successes, it's the number of individuals that have a certain characteristic. Whatever that characteristic is we're looking for, that is what our p hat is. We would call this a sample proportion. You'd call it a p hat. We call it a point estimate. So if they ask for point estimate, that's what you're looking for. So I'm going to find this first point estimate for you, and then I'm going to have you find one. So in the Quinnipiac University poll conducted in May of 2008, 1,745 registered voters nationwide were asked whether they approved of the way George W. Bush is handling the economy. 349 responded yes. We're going to get a point estimate for the proportion of registered voters who approved of the way George W. Bush was handling the economy at that time. So the solution is p hat equals 349, that's how many people approved, over 1,745, that's the number of registered voters who were asked that question, equals. So 349 over 1,745, so 0.2. So 0.2 was the proportion of people who approved of the way George W. Bush was handling the economy. So that is as simple as it gets. That's how we find the p hat. So I would like you to find the p hat on this one. The Opinion Dynamics Corporation conducted a survey of 1,000 adult Americans age 18 or older and asked, are you currently on some sort of a low-carb diet? Of those surveyed, 150 said they were on that low-carb diet. I want you to find that point estimate for the proportion of Americans age 18 or older who are on a low-carb diet. Go ahead and pause this, find that, and come on back. Okay, I'm hoping you did that. So we have 150 said yes they were, so my p hat would be 150 over the number polled. We polled 1,000 Americans 18 or older. So we just put that in the calculator. Whoops. 150 divided by 1,000. So that would be 0.15. I don't know why I put that in my calculator, but it is what it is. So 150 divided by 1,000 is 0.15. So the proportion of Americans age 18 or older who were on the low-carb diet was 0.15. Okay, obviously this does not stay this easy. We're going to take this a step further. So, according to a Time poll conducted in June of 2008, 42% of registered voters believe that gay and lesbian couples should be allowed to marry. We're going to describe the sampling distribution of the sample proportion for the sizes n equals 10, 50, and 100. This is going to look very familiar because we just did this with the sample mean. This will look very familiar. We're going to create histograms with simulations on the following slides. So with our n equals 10 sample size, take a look at this. It looks like it is skewed right just a little bit. It's not quite a bell curve, but it is somewhat close. My mean is 0.426. Standard deviation is 0.160. Let's look when our n gets larger, when our sample size gets larger. So here my sample size is larger. As you see, the spread of my data is less, and we have a little bit better bell curve. My standard deviation is significantly smaller. So basically what we're doing here, let me explain exactly what's happening. So I am going to poll 100 people and ask them, what is this we're doing? Ask them if they believe gay and lesbian couples should marry. So I'm going to poll 100 people, and then I will take whatever that proportion is. I'll find my p-hat for that 100 people. Find my p-hat, and we would plot it here, and then take another 100 people and ask them the same question and get the p-hat. So what this is this is a graph of all of those p-hats. This is a graph of all those proportions. So we are finding the proportion of the proportion, basically, because I took 300 sample proportions. So I took the proportion of 300 100-person polls, and then I put all of those here, and those sample proportions get closer and closer to a nice bell curve, and my standard deviation gets smaller and smaller. Look at that. Look how much smaller each one is. So as my sample size gets bigger, as my n gets bigger, you can see that it is getting more and more normal, and my standard deviation is getting smaller and smaller. And I kind of just say that right here. So as the sample size of n increases, the shape of the sampling distribution of the sample proportions becomes approximately normal. The mean of the sampling distribution equals the population proportion. So my p-hat, not my p-hat. So my mean, my mean is going to equal p. P is the proportion, is the population proportion. And the spread, the standard deviation of the sampling distribution is going to get smaller and smaller as n increases. And I already said that, but I can't emphasize that enough. Let's do some examples, and maybe this will help you. Okay, so our sampling distribution of p-hat. So these are the things that we have to have in order to use this math. And unfortunately, some of my symbols are not showing up. I don't know what the heck is wrong, so I'm going to have to fix these. So this is my mu of p-hat equals p, and my sigma of p-hat equals 1 minus p. There we go. Okay, so first, the shape of the sampling distribution of p is approximately normal if, so you guys saw this before, np times 1 minus p has to be greater than or equal to 10. You may be asked this on a test. You're going to want to pay attention. And this is really ugly. I'm going to try to fix it. So the mean of the sampling distribution, so my mean of p-hat equals p. So whatever the population proportion is, that is what we're going to use for mean. So whatever that population proportion is, that's our mean. So our standard deviation, this is the standard deviation we are going to use for this lesson when we are dealing with the proportions. When we are dealing with we're dealing with the sample proportions, we are going to use this new standard deviation formula right here. P, the square root of p times 1 minus p over n. This is another new standard deviation. with the sample proportions. The sample means has that other one. This is for sample proportions. Okay, let's move on. So the model on the previous slide, so we require that our sampled values are independent. When sampling from a finite population where we can assume that the sampled values are independent if the sample size n is no more than 5% of the population. So whatever population we're using, our sample size n cannot be larger than 5% of that population. The reason for this is if we had a larger sample size, the likelihood of having overlap of our sample values or having people that that interact with each other that would cause the sampled values to not be independent. So remember we were talking about independence before, and that remember the two women living in the same apartment building, those deaths would not be independent. So if our sample size is small enough, it is smaller than 5% of the population, we can assume independence. So once again, let me fix this because this is not pretty. So regardless of whether NP times 1 minus P is greater than or equal to 10, the mean of the sampling distribution of P hat is P, and this is the standard deviation. Even if we don't get our NP times 1 minus P is greater than 10, we are still going to use this mean and this standard deviation. You're not going to really encounter that though, so I wouldn't worry too much about it. Okay, let's do an example of the math that you might find on your homework. So according to a time poll conducted in June 2008, 42% of registered voters believe that gay and lesbian couples should be allowed to marry. Suppose that we obtain a simple random sample of 50 voters and determine which voters believe that gay and lesbian couples should be allowed to marry. We're going to describe our sampling distribution. So what that means is that we are going to we're going to find our mean and our standard deviation, and we are going to talk about whether or not this is bell-shaped. We're going to look at all of our important stuff. Hold on a second here. I will show you what it means to describe that sampling distribution. So first, whoa. Sorry about that. Okay, so first, the sample of n equals 50 is smaller than 5% of the population size. So 50 people definitely is smaller than 5% of all the registered voters in the U.S. Next, we've got our NP times 1 minus P. We got 12.18. So yes, that's wonderful. That is greater than or equal to 10. So the sampling distribution, so we have that our mean is 0.42 because we got that 42% of all voters. So because our P was 42%, our mean is 0.42. So now we need our standard deviation. Oops, that's not the right one. Standard deviation of P hat is, so it's P times 1 minus P, so 1 minus 0.42 divided by 50, and then take the square root of that. So our standard deviation would be 0.0698. This is really close to the standard deviation that we found on our simulation in example 2. So that's really good that we got really close to that using our math. So I'm going to, on the next slide, I'm going to give you a scenario, and I want you to, number one, make sure that the sample is smaller than 5% of the population. Number two, figure this out. NP times 1 minus P, is that greater than or equal to 10? That's something you're going to need to know. Next, figure out your mean and your standard deviation. Here's your scenario. Based on a study conducted by Gallup organization, 76% of Americans believe that the state of moral values in the United States is getting worse. Suppose we obtain a simple random sample of n equals 60 adults. So, okay, I just lost my train of thought. So if n equals 60 Americans and determine which believe that the state of moral values in the United States is getting worse, describe the the sampling distribution of the sample proportion for the Americans with this belief. So first, is it less than 5% of the population? Is it normally distributed? Find the mean, and find the standard deviation. So go ahead and pause and find all of those things, and then come back and we will talk about it. Okay, so I'm hoping you paused and you figured that out on your own. So first, 60 is definitely less than 5% of all Americans. 100%, no problem on that one. So next we're going to do NP times 1 minus P. So that's going to be 60 times 0.76 times 0.24. We're going to get that information, and one would think that I already would have had this done, but sometimes I am just dropping the ball, and that did not work. 60 times 0.76 times 0.24, and I got 10.944. That is greater than or equal to 10. So we're good there. So we have a normal distribution. Next, we need the mean. Our mean here is 0.76 because remember, the mean equals our P, our probability, our proportion right there. Next, we need our standard deviation. So that's the square root of P times 1 minus P over N. So that would be the square root of 0.76 times 0.24 divided by 60. So our answer here would be approximately 0.00551. That would be my standard deviation. And that's it on that. Now we're going to take this one step further. We are going to talk about actual probabilities of things happening. This is kind of like what we did at the end of the other, trying to find out, actually put this to use. And so let's go. Here is our next problem. Whoops. According to the Center for Disease Control and Prevention, 18.8% of school-aged children aged 6 to 11 were overweight in 2004. So first, in a random sample of 90 school-aged children ages 6 to 11 years old, we want to know the probability that at least 19% are overweight. So 19% or more are overweight. Then after that, we're going to look at, suppose a random sample of 90 school-aged children aged 6 to 11 years results in 24 overweight children. What might you conclude? So let's take a look at this first. Whoops. So N equals 90 is less than 5% of the population size. We're good. NP times 1 minus P, we have 13.7, so that is greater than or equal to 10, so we are normally distributed. So now we need to find our mean and standard deviation. Our mean, because it was 18.8% are overweight, we have 0.188. That is our mean. Take a look at the standard deviation. Even though my things are not showing up correctly here. So we did 0.188 times 1 minus 0.188 over 90 to calculate our standard deviation. So our standard deviation right here is 0.0412. In order to determine, let me see here, fixing my numbers. In order to determine the probability that at least 19% are overweight, we can use our z-table. I'm not going to pull my z-table up right now. Can use our z-table to get our z-score. Once you get your z-score, when you look on your z-table, you would have to do the 1 minus, because remember the z-table gives you the left side. It gives you that number and lower, and we want that number and higher. So with our z-table, we got 0.4801. So I'm going to put in my calculator really quickly here, because I forgot to do that before. Comma 0.188, comma 0.0412. So with my calculator, I got 0.4806, which is really close to 0.4801. So that's because I rounded this. I rounded that to 0.05. So it's really important to remember it's normal CDF. You'd put lower bound, upper bound. The standard deviation, sorry, this is your mean right here, 0.188, and that was really messy how I did that. The mean is 0.188. Remember that the standard deviation that you are using is this one here. You're using the standard deviation that you calculated. So let's answer the second question. So we got our first question, we wanted to know, what is the probability at least 19% are overweight? So our probability at least 19% are overweight is about 0.48. So we about 50-50 that 19% are overweight. Let's take a look at the second question. So we got p hat is approximately normal with mean 0.188 and standard deviation 0.412. I kept this because I'm going to need it with my next problem. So what I want to know right now, what I want to know right now is we took a random sample of 90 school-age children, ages 6 to 11, and result in 24 were overweight. We want to know what you might conclude. Okay, so in this case, what I need is I need my p hat because I need to know, so my p hat right here, so I took my sample. So once you have a sample, so we have all of our, found our standard deviation, we found our mean, we found all of that. What we need to do now is with our sample size was 90 school-age children. You can't see this very well. And 24 resulted in overweight. We want to know what we can conclude from that. So what I'm doing here is I'm taking my p hat, so my p hat would be 0.2667. And I can use this, I can find my z-score of 1.91, and I can find out the probability that I can find the probability that z is greater than 1.91. We're always going to do greater than because basically we're looking at that point. So what you're going to do, put normal CDF, 0.2667 to infinity. This is that E99. I want to know the probability that that happens, the probability that this could happen. And 0.188 is my mean, 0.0412 is my standard deviation. So this is the number that's going to drive us right here. So when we found the probability that a child, that 24 of them would be overweight is 0.028. 0.028. So what this means is that if out of 100 people, we would only expect 3, or 100 samples, we'd only expect 3 to be overweight. Sorry, that is not exactly what's happened. So 3 samples. So basically what this is saying is if I took samples size 90, 100 samples of size 90, we would only expect 3 of them. Sorry, we'd only expect 3 of them to have a sample proportion of 0.2667. So basically, if this number right here is less than 5, that's really ugly and it's hard to see. If this number here is less than 5%, that doesn't work either. I'm going to quit doing that. If this number right here is less than 5%, you are going to say it is unusual. It is an unusual sample if our true proportion is 0.188. So basically just look for that 5%. If that ends up being 5% or less than 5%, then you would say it's unusual. Okay, so I have a scenario for you right here. Sorry. I have a scenario for you right here, and I would like you to do exactly what we just did with this last one. If you need to go back, go back. So according to the National Health Statistics, 15% of all Americans have hearing trouble. In a random sample of 120 Americans, what's the probability that at most 12% have hearing trouble? So let's go ahead and pause this, and I want you to find the mean and the standard deviation, and I want you to find the probability that at most have 12% hearing trouble. And then after that, go ahead and so just do that one first, and then we'll come back and we'll go over that, and then to make sure you have the right numbers before you do B. So go ahead and pause this, figure out the mean, the standard deviation, and the probability at most 12% have hearing trouble. All right, so I'm hoping you did that. So what we have here is we have our mean would be 15%, so our mean. But before we do that, 120 Americans is definitely less than 5% of the population. Then I want to do NP times 1 minus P to see if that's greater than or equal to 10. So I have 120 times 0.15 times 0.85. Let's see what that is. That would be 120 times 0.15 times 0.85. And I got 15.3. So we're good there. Standard deviation. So my standard deviation would be square root of 0.15 times 0.85 over 120. And we take the square root of that. So once again, put this in the calculator. And I got approximately 0.0326. Good. So now I've got my mean and my standard deviation. I could do this with z-scores, but I am not going to. We're going to do a normal CDF, and at most, so we're looking for the probability that, probability at most, so it be greater than or less than. So this is less than 12%. So I would do normal CDF. And it's less than, so we do negative E99 to 0.12, comma, 0.15, comma, 0.0326. Put that in your calculator. And I'm totally running out of room here. So it's negative E99, 0.12, comma, 0.15, comma, 0.0326. And I get about 0.1787. So this right here is the answer to the top. This is the probability that at most 12% have hearing trouble. So that's pretty small. It's a pretty small probability. So now what I would like you to do is I would like you to pause this again, and I want you to take a look at this. So suppose that a random sample of 120 Americans who regularly listen to music using headphones results in 26 having hearing trouble. What might you conclude? So remember to find your p-hat and use that p-hat with your normal CDF and the standard deviation that you already calculated to determine, just to see what you might conclude from that. So go ahead and pause this and come back and we'll talk about it. All right, so I'm hoping you did that, hoping you calculated that. So what we're looking at is we need our p-hat. So our p-hat is 26 out of 120 had hearing trouble. So 26 divided by 120. So 0.2167. So this is what I got for my, approximately for my p-hat. So I need to use that p-hat with normal CDF. CDF. And do 0.2167, comma, E99. And I'm going to run out of room. 0.15, 0.0326. Let's put that in the calculator. Comma 0.15, comma 0.0326. And I got equals 0.02037 or 38 approximately. So what might I conclude? So I got that, let's see here. So that means the probability out of, if I took 100 of these random samples of 120 Americans and found the p-hat of each of them, of each of my results, I would only expect 2 of them to have the higher hearing trouble. I would only expect 2 of them. So there's only a 2% probability that it would have that much hearing loss or more. So basically what we can conclude here is that possibly the music, the headphones would have caused hearing loss for these people, because our original statement had nothing to do with headphones. So we can say here that possibly listening to the music in headphones is probably causing that extra hearing loss, because there's really only a 2% chance of that happening. So that's not good. So we might have to go back to that and talk to them about listening to headphones, and maybe they're listening to it too loud. I don't know. But that's what we can conclude from that. I know that this section is a slight bit confusing. Make sure you send me those emails and messages. A lot of you have been really good about that, and I can help walk you through it even more. It's a lot easier when you have questions, individual questions about things, for me to walk you through it and talk to you about it. So that's the end of this one. Have a great week.